All right, hi everybody. Welcome back to our 10th C++ programming lecture. Yeah, we are pretty much almost done, content-wise at least. So if I recall correctly, excluding today's lecture, we have, I don't know, 3 or 4 lectures left. Yeah, we are making really good progress. So let's have a look at what we're going to discuss about today. So I have some more slides on object-oriented programming, so we will talk about a few more features that you're made to use in the context of object orientation. We will briefly talk about type conversion and aka type casting and why that might be useful to you. And at last, we will talk about file I/O, so input and output, how to get data into your program. Usually, it's a 3-step process, right? So you read some data into your program, you process this data, and at some point, you're writing that data back to a file or whatnot. And so we will be discussing file I/O today as well, as a very important part of everyday programming, really. And also we have hopefully a nice interesting exercise on file I/O, so I try to come up with something interesting. All right, but first of all, let's finish on object-oriented programming. So when we have a type hierarchy and the parent class has a virtual function, then of course we as a child class can override that virtual function and we can specialize it to do some certain tasks. And the question sometimes arises, can I actually also call my parent's functions implementation? And the answer is of course yes, that's possible of course. But what does the syntax really look? So let's have a look at the syntax. So let's have a brief example. We have some struct type A. We have a virtual destructor, which we just default. And we have a virtual function void, which in our case here just prints A to the command line. Then we also have a type B, which is a subtype of A. And it overrides the function and it prints B to the command line. And to complicate things further, let's also have a struct type C, which inherits from B, so one more inheritance step. And it again overrides the function and prints C to the command line. So what we can do now, of course, in programming is we can create a new variable C of type uppercase C. And of course, we can call its member function. And if we call that member function, C will be printed because the allocated type is uppercase C, and therefore C's specialization of that function is being called, which again prints C to the command line. However, it's also possible to call one of the parent's specializations. So what you could do, for instance, is how you would type it is your C dot and then the name of the parents class or parents type, which here B, for instance, is chosen, and then colon and the member function's name, which is function here. And so this line of code, this piece of code here would call B's version of function, which would print a B to the command line. And then, of course, what we can also do is we can say, please use the functions implementation of my parent A. So you would type c.a colon function, and it would print eventually A to the command line. So that's the idea basically. All right. Then something else which might be important to you whenever you solve more complex problems. The question arises, do I use inheritance or do I use composition? I mean, both of the concepts are very similar. Some programming languages, such as Go, for instance, do not even include inheritance, so there is no inheritance in Go. if you wish to achieve something like inheritance, you would use composition instead. So let me give an example on what that really means. So yeah, again, my point is sometimes composition might be more useful than using inheritance. And really, I can't give you the answer. It highly depends on the problems that you're going to solve, that you need to solve, and the problem's nature, really. So I can only provide you with the means to solve problems, and then you have to decide, yeah, what is the best mechanism to solve a given problem. And the idea of inheritance is that you, rather than having a guitarist class and a drummer class and maybe okay, that should be vocalist here. And then you would have a class band which inherits from the guitarist. So a band can do all the stuff that a guitarist can do. And then the band class would also inherit from drummer, such that it is able to do all the stuff that a drummer can do. And the band might also inherit from vocalists. So you have some singer in your band that you inherit all the functionalities of that singer in your band. And then you have a band really, which is a class which inherits from all the individual other classes to make use of its features. I mean, that would be the typical inheritance way. What we have depicted here in that picture is this is called composition. So we still have individual data types here in order to implement the individual features. So here the vocalist would be able to sing some nice songs. Then we would have a drummer, and we would have maybe some guitarist as well. And we can also compose them such that we have a class band, and the band now has individual members. So it has the subtypes. It doesn't really use inheritance, but rather it has data members of the required functionality. So a band must have a guitarist, maybe, must have a drummer, must have a vocalist. Yeah, rather than inheriting from all those classes, just have them as data members, really. That would also be possible. And in languages such as Go, you would use composition here rather than inheritance. Okay, so that's an alternative I wanted to present you. What else can we compare? So we can also compare templates versus inheritance. So let's talk about the differences between templates and inheritance. So when to use what? That's some probably good question which we should answer. So both of those concepts are orthogonal to each other. So that means you can use templates and inheritance together. And most real-world software projects also do that. Here's an example of the Phaser framework which I developed in my PhD. So it's a static analysis framework, but it doesn't really matter. I just wanted to show you an example how a class can look like and how how inheritance and templates can be used together. So here we, for instance, have a class in IDE tabulation problem. We inherit from some other classes such that we inherit all of their features and functionalities. And anyhow, I can still just have it as a template. I can still have some template parameters which my IDE tabulation problem receives, and it can also propagate those template types into those other classes which it inherits from. So such a thing is also possible, so you can use both concepts or mechanisms together. Sometimes that's very, very useful. So what inheritance is and what templates are, so let's see. So inheritance, as presented last time, is kind of vertical, so from bottom to top, or the other way around, depending on how you want to see it. So it's from an abstract type going to a more concrete type. And you can then, by overriding virtual member functions, you can specialize your subtypes to model a certain problem. Whereas if you use templates, it's really kind of horizontally, so it defines parallel instances of code. So whenever you have a template function or a template class or whatnot, so it acts as a kind of code generator. So whenever you plug an int, you will have a new version that works on integers. If you plug in a double, you have a new version of whatever you define as a template that works for doubles. So that's basically parallel. Because the general functionalities in templates still remain the same. It's just basically some type placeholders, and it will generate the respective version for the types that you give that template mechanism. So that's basically horizontally, whereas in inheritance you can really go from abstract to more concrete, and then you can specialize, and also you can change the behaviors. That's my main point, I guess. Yeah, let's have some examples. So last time I already presented that example to you. So if we have a look at shapes, so that would be in our case that was the most abstract type. Then we would have some subtypes as well, so triangle, right angle, triangle. And for templates we had the example where we sorted some stuff, so we could sort integers, we could sort doubles, so everything basically which overloads the smaller than operator could be sorted. Eventually we also introduced the predicate, so you could basically sort anything. But here using templates, I mean, sorting still remains the same. So I mean, the algorithm, how to sort is always the same. What you just plug in are different types. Whereas again, in inheritance, you can also specialize the functions and make your subtype behave differently from your supertypes. Inheritance is also a runtime abstraction. So yeah, that's probably good enough, whereas templates are a code generation tool. And here in inheritance we have a kind of dynamic polymorphism. I told you whenever you have a virtual call site, so the v-table is looked up, so it is determined to what that type, what the runtime type is, and then the corresponding function implementation is being called. Whereas in templates you have just a static polymorphism, so everything is fixed statically at compile time, and then you can't change any behavior at runtime. Yeah, and again, both can be used in combination. I already showed you the example on the last slide. And here again. Okay, so that's my point. Okay, that would be pretty much it. We now have to discuss typecasting, which you can also use in a nice way for object-oriented programming. So let's see how that works out. First of all, what is typecasting? That's pretty much typecasting. I mean, conceptually, you have some data in memory, which is just, yeah, a bit string and a variety of bits which make up your data. But then this bit string, that piece of memory really, or that value that is stored in memory in terms of ones and zeros, its semantic meaning highly depends on the data type. So the type basically gives meaning, gives semantics to a certain value, to a certain bit string in memory. And yeah, here on this example we have the same actor, but kind of in different roles. So yeah, he is semantically different in his roles in those two movies. What is it? Lord of the Rings and Star Wars, I believe, right? Yeah. Okay, so casting is the mechanism of type conversion. So what you can do in yeah, I guess almost all programming languages, you can interpret data in a different type, really. So you can convert its type. Sometimes that's quite useful. Also, if you haven't already noticed, that happens implicitly for most primitive data types. If you ever need to use explicit typecasting, be very careful not to do something stupid or not that wise. So yeah, be careful. Usually it holds that the type system is your friend, so you don't wish to randomly cast data from one type to another data type just to make things work. So usually things have types such that you don't make mistakes. So the type system does prevent you from making mistakes by associating types, by associating values with types. That's the main point here. So how you would do it in C, and I would recommend to not use the C style casting, because C++ has some more decent mechanisms to do typecasting. But how you would do it in C is you would have an expression which of course evaluates to some type. So an expression always evaluates to some type. And how you do it in C is you have in parentheses, you have your new type. And then whatever that expression might evaluate to, and whatever that expression has as a type, we will now interpret it as the new types that we specify here. So maybe, do we have an example? I hope so. So what my recommendation is, don't use the C style cast, use the C++ version. If you look up the casting rules for the C style cast operator, it's a nightmare really, and C++ is somewhat more explicit about casting, so it's in general safer to use, I would say. Here we have some examples. So what we could do is, here in this case I'm using the C style casting again, yeah, shouldn't do that. Here we have a double, right? So if we have floating point number, the compiler usually, unless you specify otherwise, just interprets that value here as a double data type. It associates the data type double with that value. And here we can say, yeah, please take that double, or whatever that other thing that might be, and interpret that as an integer. So take that thing here, take that value and make it an integer. And how it works in C and also C++, if you cast a floating point number to an ordinary integer, it will just cut off after the decimal point. So if you wish to mathematically floor or seal, just use the floor and seal function, which you can find in the C math header. But if you just directly cast an integer, it will just cut off the decimal figures. What else can we do? We can also do stupid stuff. What we can do is we can have a huge integer, and we can then just so this would be interpreted as an integer, if I recall correctly here, by the compiler. And we can also say, yeah, compiler, take that integer value, the value of type integer, and cast it in a short, cast it to a short type. The problem is, unfortunately, short cannot basically fit such a large number here. So what would happen is here we would overflow. So you can also do stupid stuff by using casts. So be very careful. What's okay is we can have an integer 14. Yeah, of type integer. The compiler would default make it an integer literal, and here we can say, yeah, compiler takes that integer literal and change the type integer to double, and then D would contain the value 14.0. So that seems reasonable. That's not dangerous at all. And if you use different typed values in a computation, the compiler tries to cast to the most precise representation that is involved in that computation. So let's have an example. So what you could do, for instance, is you could have a double value, 12.5, and you multiply it by an integer value, which would be 12 in this case. So the right-hand side is an integer, the left-hand side is a double. So the compiler would, before it performs that operation, the compiler would implicitly cast that integer to a double, because for the overall computation that would be the more precise representation. and then you would have this expression evaluate to a double, which you then store perfectly fine in the variable p. So some casts happen implicitly, which are fine, hopefully, for the most time. Some casts can be forced explicitly. Here you can also do stupid stuff, so be aware of that. Think about if it makes sense, if you should do that. Your compiler also complains sometime or emits some warnings, and I recommend to read the warnings, compiler warnings, carefully. Okay, here's some examples. And now that we have casting, we can really use it in an object-oriented manner, so to say. So we can use a dynamic cast in the reference version. There's also a pointer version of that. I will show you both, but let's maybe start with the reference version. Yeah, again, this goes hand in hand with OOP. So let's have some example code. What we can have is, let's define ourselves a struct A, virtual default destructor, and some virtual function f. And then we have a struct B, which inherits from A. We have a struct C, which inherits from A, and we have a struct D, which inherits from B and C. Careful, this might cause the deadly diamond of death problem. So if you have multiple inheritance, you may form that diamond structure, and sometimes the compiler doesn't know what function to call, so be aware of that. But again, last lecture I also told you how to fix that problem. Anyways, so let's have this kind of small type hierarchy here. And then let's have some uses. So what we can first of all do is we can just allocate a variable onto the stack. Let's have a variable d of type uppercase D. And this is, of course, the most derived object in the current type hierarchy here, which is shown on the left-hand side. And we can now do basically an upcast, really. A dynamic cast might be or may be used, but it's not necessary. So because D is the most derived stuff, what we can do is we can also have a reference. So we can create another reference variable A of type uppercase A ref, and we can assign D to it, basically. And then we have reference A variable A, which actually refers to something which is of type D, so runtime type D, static type A ref. And this works perfectly fine, because, I mean, recall that D, the variable D, is of type uppercase D, and uppercase D is also kind of an A, because D inherits from B and C, and both B and C also inherit from A. So practically, D is not only type D, but D is also type C, type B, and it's somewhat type A. So this works perfectly fine, and this is what we called an upcast, because now you have a reference of one of the parent types to that more derived object, so to say, to that more derived type. So what else can we do? We can also have a downcast. And if we use a downcast, we need to check, we need to do a dynamic cast. And I'll tell you why that is in a second. So now what do? What we do is we put that variable A, which is of type A ref, we put it into the dynamic cast operator. So you put it in the parenthesis. Here in the angular parenthesis, you tell the dynamic cast to which thing you wish to cast that to. So you give it something of type A ref, and you say, yeah, basically try to make me a B ref. And then you have a B ref to that underlying A ref, which is in fact, which refers to a D. So why do we need the dynamic cast? So because we put something in which is of type A ref, we can't be sure that it is also of type B ref. Because, for instance, do we have an example? How How can I explain that in a good way? What you put in aref is something more concrete, more abstract, and now we wish to make it something more concrete. So if the aref here refers to something which is more concrete than A, in fact, for instance, which is concrete in the sense that it is of type B, which D eventually is, so D is also B and C, that dynamic cast works perfectly fine. And then if the dynamic cast succeeds, we have a bref, which refers to the underlying value D here. But a dynamic cast could also fail. And if a dynamic cast fails, then an exception is thrown. So I will present you some examples on that on the next few slides. So a dynamic cast, if you try to go from abstract to more concrete, this can succeed, of course, if the underlying runtime type, in this case D, fulfills that type, basically, if it implements also a B, and I mean D also is a B, so that works perfectly fine. But it might also fail, because you might be putting something in which just does not implement that type, or does not inherit that type, and then the compiler cannot make up stuff, right? So if you have some concrete, if you have a more concrete type D is obviously more concrete than A, because D implements some stuff and it also implements A, so D is more concrete than A. And if you just have a aref, which is more abstract, and let it refer to D, that's perfectly fine, because we can basically just ignore information. What the dynamic cast requires us to try to gain more information, and this only really works if the underlying runtime type provides that information. And if it doesn't, the dynamic cast fails, an exception is thrown, because the compiler cannot make up stuff. All right. And we can also have a side cast. So we can now also, we have that bref variable new C. We can also cast it to a cref type, which we then call new B. And this also works perfectly fine, because the underlying data is of case uppercase D, is of type uppercase D. And D also implements C, so we can also sidecast it from a bref to a cref. Perfectly fine. That works. Let's discuss maybe the next few slides, and hopefully you get the idea of what that concept is all about. So first of all, maybe the pointer version, and here you maybe already get the hang of it. So you can not only do that principle, the dynamic cast, with references, as we did on the last slide, but you can also do it with pointers. So again, let's have an example. Let's have a struct base, and we have give it a virtual destructor, which we set to default, and we give it a virtual function f. And then we have a derived type, which derives from base. And what we can now do is we can have a base pointer, b1, and we let it point to some dynamically allocated value of type base. So here the static type is base pointer, and the dynamic type, because new, if we allocate with new on the heap, that happens dynamically, the dynamic type is base. And this works perfectly fine. You obtain a base pointer and you put it into a pointer of type base, b1 namely. That works perfectly fine. What you can now try to do is, using a dynamic cast, you could now put in the base pointer b1 and try to cast it into a derived pointer. Here this is a construct in that if, so you have a derived pointer d. You try to dynamically cast the b1 to a derived pointer and store it in that d variable. If that thing, the overall expression here, evaluates to the null pointer, then the cast has not been successful. So whenever the dynamic cast gives you the null pointer, in case you're using it in the pointer version, then the cast could not be performed. If it's a pointer which is not the null pointer, then the cast has succeeded. So here we can just wrap it in an if. So if d eventually is something other than 0, then the cast was successful. And my question now to you is, does that cast succeed? Does it succeed? And the answer is no. Because here, again, b1 is a base pointer, which points to some allocated type base. But we can't just make up stuff. So derived is something more concrete than base. And the other way around, base is something more abstract than derived. So we cannot just make a derived thing out of a base pointer. That doesn't work. Let's have another example. What we can also do is we can have a base pointer b2 and let it point to some value of dynamic type derived. So we can allocate a derived value, so something derived, on the heap, and this gives us a derived pointer which we store in a base pointer, and that works perfectly fine because observe that derive inherits from base. So that means derived is also some kind of base which allows us to store a derived pointer which we obtain from this new expression here. We can store the derived pointer into a base pointer. That works. And now we can have another dynamic cast where we try to cast the base pointer into a derived pointer to access maybe derived extended functionalities. So maybe derived also implements some more stuff, and if we then wish to access it, we need to downcast it to derived. And this cast here would actually succeed because the derived cast looks up what the actual allocated type of that pointer is. b2, of course, is a base pointer, but the value that it points to is of allocated type derived. So this cast succeeds, and you can make that base pointer b2 into a derived pointer d. And so you will enter this branch because d eventually is something which is not the null pointer. So this message will be printed. And also you could now access derived, maybe extended functionalities. So maybe if derived would override f and would also in addition implement a new function g or whatnot, you are now able through the derived pointer d to access the functionalities, the extended functionalities. That's the idea basically. Again, it's pretty hard to explain that kind of stuff without having somewhat meaningful examples. But again, last lecture I already showed you that at universities, unfortunately, you almost never work on projects that are that big and complex that you need those kind of mechanisms here. So yeah, I hope you forgive me. I just show you the basics, how it works, how the mechanisms can be used. And hopefully if you work on larger projects later on, you can make good use of those concepts. But those concepts here, those mechanisms are really, really useful. So that's very important to understand here. And of course, we also need to delete B1 and B2 such that we get rid of the dynamically allocated objects here. So we can also check is a relation with a dynamic cast. So this is called, with the dynamic cast you check basically an is a relation. If the dynamic cast succeeds, then one thing is also another thing. So a triangle, if you downcast something from type shape to a triangle and the cast succeeds, then the underlying type was also not only a triangle but also a shape. Okay, let's have another example. So check is a relation with dynamic cast. So again, let's build a small type hierarchy. And you have to use exceptions in the reference version, and you have to check for the null pointer in the pointer version. Let's have an example. So when you try to dynamically cast something, this cast may also fail depending on what the allocated type of that thing that you put in is. So in this case, D that you give in is of allocated type uppercase D, which is also an A through inheritance here. So this cast would succeed. But if you would put in something else which is not really an A, or which cannot be casted to an A ref, then an exception would be thrown. And you would usually you need to wrap it in try catch to to recognize if a cast could not be performed correctly. And in the pointer version, here is the pointer version, you would just check for the null pointer. So if the overall expression here evaluates to the null pointer, then the cast failed, and otherwise if that is something other than the null pointer, then that cast would succeed. That's the idea. And yeah, also we need to delete what we allocated here, so very important. There's one more, two more casts, or three more casts actually. So let's see if we have slides for all of them. So you can also use const cast to cast constness away, and this is pretty much like that picture here. So usually you should not cast constness away because things are const for a reason, and the reason usually being that thing should not be changed. That's the meaning of const, right? But you can also cast it away. And you can cast constness away, or you can remove constness when the underlying type is not const. So what does it mean? Maybe let's have an example. First of all, maybe let me tell you that this is also considered bad style, so you shouldn't do that. You should not work against the type system, because the type system is the thing that should prevent you from errors, from making errors. Exactly. So yeah, only please use it in some rare or extreme situations. If I recall correctly, we have some example in today's lecture where we actually use a const cast to pull off a dirty hack. I will show you that example and then refer to that const cast here, but usually please don't use it. So how could we use it, even though you shouldn't do it? It's probably good to know. So what we can do is if we have a function, for instance, which receives a const int ref, and the parameter's name is I, usually within that function we can only read from that integer I. But what we usually can't do is we can't write a value to I because it's a const int ref, it's a const ref. Right? But what we can do here is we can use the const cast, and we say, yeah, just take that ref I and cast it into an ordinary integer reference. So here we remove the constness. And this allows us, because it's just a plain int ref, we can then write some integer value to it. That's the idea. Maybe let me also give you another example. So here, let's have integer I, which we initialize to 3. It's also declared not as const, so it's a plain integer, which can be modified. So the underlying type is non-constant. And we now can have a const ref, which we call a cref for const reference I, which refers to the integer I. And of course, if we would try to write some data into that cref reference, it would fail. The compiler would complain. It would statically bail out and tell you, yeah, you cannot write something through a const reference. But what you can do, what you could do is you could cast the constants away and make it an int ref, and then you would be able to write 4 in it. And this would work because the underlying integer that everything refers to, I, is a plain integer. So it's not constant. And then you can print and it would really show 4. Also, let's have another non-constant integer, which we initialize to 1. Let us call the modify function. And it will write through that const ref here by using the const cast. And after that function call has been evaluated here, the other variable will contain the value of 100. That's the idea. Okay, please don't do it. So what else do we have left in C++? We also have a reinterpret cast. That converts a type by reinterpreting the underlying bit pattern. That's probably the cast operation or the cast operator that you need the least, I guess. It just returns a different interpretation of bits. Let me show you an example. So here we have a number of bits. If you start your bit string here with OB, the remaining value here will be interpreted as binary. So you can directly type in binary literals by prefixing with OB for binary. Then you give a bit string of 1s and 0s, and you store that bit string in an integer variable by the name of bits. And by the way, I believe this is 394 in decimal if you're interested. Okay, so what could you do with it? You could now also reinterpret those bits here, which sit in the integer variable, and reinterpret them as a double ref. And this would give you the following double value. So I mean, that's not of any particular use. I just wish to show you how you could use it. Yeah, you can print stuff afterwards, of course. Again, this is really needed. I'll just show it to you for completeness. Some examples are if you have to implement some device drivers, and then the reinterpret cast might be useful. And ordinary software engineers don't have to implement device drivers usually. Or if you need to fiddle with some shared object libraries, again, that's also somewhat more advanced stuff, and I don't have the time or chance here to explain to you how that works in all great detail. So those would be some example scenarios where a reinterpret cast could be used. And at last, I believe that's the last cast I'm going to present. I believe then we are also complete pretty much. And the last thing is the static cast. And this is just an explicit cast. You can cast basically, as example, you can cast in hierarchies and type hierarchies where you don't have virtual member functions. You can also use the static cast if you wish to perform some type conversions between primitive types. That's also perfectly fine. And this is yeah, more or less somewhat the equivalent to the plain old C style cast. But rather you should now use the static cast here. And this would also be a fine application for static cast. Here you have an integer 42, and maybe you wish to make it a double, or you wish to convert it in a double, and here you statically cast that integer value I in a double D. So D would afterwards carry the value 42.0. But again, there are also some implicit conversions going on. So if you try to write floating point literal into an integer, then you have just a cutoff of the significant figures. So J would be 3. You can also then put a thing of type integer into a double directly. So here at this place also we would have an implicit cast. And E would carry the value of 3.0. And of course, also you have a Boolean usually used as in context of implicit casts. So whenever you put something which is a non-zero into a bool, it will evaluate, or it will carry the value true, and only if you write 0 to something of type bool, it will be evaluated to false. So that's the idea pretty much. Okay, some more miscellaneous stuff, but just for completeness. There's something in the language. C had it already in the language, and that's also why C++ just inherited it. It's a mechanism called goTo. So really like go to a certain location, which is a somewhat evil mechanism that you should not use if possible. So please avoid it if you can. So yeah, goTo is considered as an evil mechanism. It performs an unconditional jump to a label. We will have an example in a second, I believe. So you can have some labels in your program, and then goTo is a keyword, and then you can jump to a label, and basically you can just perform an intra-procedural jump. So a jump within a function is possible. So when should you use goTo? So you should use goTo if you would like to introduce bugs to your program, because it makes your program very hard to read and to reason about. So maintenance becomes pretty much impossible if you use it extensively. And yeah, you make your program unreadable. So those are the main reasons why to use goTo. Also, what's important here is that every program with a goTo can also be expressed in a program without a goTo, and you should probably prefer the latter one. So do prefer programs without goTo. There are some limited useful applications for that. Usually you use it if you use it at all. My advice is not to use it. Error handling, that's pretty much always a use. We will also have an example where we see some error handling which went somewhat wrong. Restrictions is you cannot jump across functions. So by using goTo, you can only jump within of one function. So you can't jump between two different functions. That wouldn't make too much sense. That would also be theoretically not possible in the ordinary usual computation models. That just would not work. If you need to use jumps across functions, you can use set jump and long jump. So I don't recommend that, and I don't explain it in any more detail here. Look it up. It's some C style stuff. 2 model exceptions, but no, just use C++'s exception mechanism, and then you're perfectly fine. So I shouldn't have said this probably. So let's have an example on goTo. So what we can do, I mean, this is a stupid example. It doesn't do anything of use, but just an application of goTo. So let's have a counter variable. Let's have a label. Whenever you use goTo, you need to add labels. So a label is just a symbol. So you just have a bunch of letters, and then it's followed by a colon. And yeah, this is now a label, which is called label accidentally. Then we can have the following. We can print the counter, which prints 0 initially. Then we have a condition. So if the counter is smaller than 10, then increase the counter, and then go to label. And this thing here now causes a jump to that label. So that means the next instruction after that go to label is we execute the cout statement here again. And we continue and continue. And at one point, of course, the counter will be 10 or even greater than 10. And if the counter is 10, we don't enter this if branch here anymore. And then we just continue our execution after the if branch. And then here we just have some nested for loops because we can. and we can check some stuff with a condition, and if the condition evaluates to true, we go to the label end loop. Otherwise, yeah, we kind of continue here to loop, and then we create another label end loop to which we then jump if that condition here evaluates to true, and then we print just a new line at the very end. So this is how you could use it. You probably shouldn't. Why shouldn't you do that? I believe that's some code implemented by Apple, right? That was pretty famous a few years ago. So you can also type in on Google like go to fail Apple SSL, and you will probably find some newspaper articles and people making fun of Apple. It was Apple, if I recall correctly. Yeah, please check if you're really interested. So, and this was a piece of code here which implemented some SSL verify signed server key exchange. So it's highly security critical. And I already told you goto is usually done for error handling. Is usually used for error handling. So you check some stuff and check if errors occurred, and if errors occurred, you go to an error handling label. But the problem here was that by copy and paste, by the magic of copy and paste, we had one goto fail too many. And that basically means, so we evaluate the thing here and update our hash or whatnot and check if an error occurred. And if an error occurred, we go to fail. But if no error occurs, because those guys were that brilliant that they don't even did the curly braces, and that's also why you should use curly braces. In the else branch, basically, or not in the if branch, we then still continue by just going to the fail label anyways. And yeah, despite the name, this always returns okay. So so I mean nothing is verified in that piece of code, which is really unfortunate. So I mean that's just rubbish, and that can lead to huge damage. So be aware of that, and probably don't use goto. And do the curly braces, my recommendation. Okay, that was interesting. Now let's talk about the last topic for today. Let's talk about file I/O, which you will also need for the current exercise sheet, at least for the first exercise. So I/O stands for input-output. So let's talk about file input and output operations. How to get huge data into and also out of your program. Usually if you call your program and it computes something of interest to you, you don't wish to give it all the data it should do computations on as command line parameters. That probably doesn't make too much sense, but rather you wish to read some data from a file and you would wish to process it and maybe even you wish to write your results back to a file. So let's discuss how that is done in C++. So yeah, use files. Data that you might wish to read or write might be small, medium, or large. I mean, those are three categories. Small is, I consider small to be everything under some several hundred megabytes. That is small. If you have some files with some 100 megabytes, gigabytes or something, that is medium. And if you have some files of size of several gigabytes or even a terabyte, that I would consider as huge. And so for each of those sizes, there might be a preferred way on how to deal with that. And I will present you those things. Yeah, I present you the most convenient ways. There are probably a million other ways to do it. Yeah, I show you the starting points, the entry points, and then you can start your way from there, I guess. Text files, binary files, yeah, we will see both. And also at last we will discuss about serialization. And then again, you can also serialize in text or binary format. Okay, so reading and writing from files is important. You have to do it at some point. But there is some but. You should reduce your file I/O to a minimum, because that's pretty much the most expensive operation that you can do on your machine. That's the slowest thing to perform. We have a memory hierarchy here, which is taken, I believe, from Wikipedia. Yeah, and of course, within your computers, within your machines, you have different kinds of memory, right? So the fastest memory that you have, also of smallest size, you only have very few bytes that you can use here. Those are processor registers. So your processor has some processing units, of course, and it also has some registers where it can store values. And those are very, very fast, but also very expensive, and you can only therefore afford them in a small capacity. So you can't store much in the registers, really. And those only really work also with power on. So once you turn your machine off, registers are killed because they need power to keep those values in memory. What you also have is you have a processor cache. So that's a particular piece of memory which sits on your processor still. It's also very fast and also very expensive. It also only has a small size, but there you can also store some more values. You can store some more data in the cache, and because the cache is directly planted on your processor, the processor can access data in the cache very fast. The second fastest after the processor registers. Then of course you have some RAM chips, so you have some random access memory, which is still fast, but nothing compared to cache. So cache is really, really fast, and those are orders of magnitudes slower. Even the random memory access, it's slow compared to cache. But it's nowadays affordable. I mean, how many gigabytes of RAM do you have in your machines? I mean, even my small laptop here has 16 gigabytes. So it's, yeah, somewhat cheap today. And it can store a medium size of data. I mean, yeah, my machine 16 gigabytes. And it also only works with power on. So once you turn off your computer, your RAM chips they lose all the data, and it's only used for storing stuff in a short term. The next thing that you can have is flash memory, USB memory, which is really slow again compared to random access memory. It's dirt cheap by now, so you can store some larger data in those kinds of memories, and also it keeps the memory even if you turn the power off, and then if you restart your computer, values will be still in there. Then you have some hard drives which are even slower, and I guess you get the idea. And at the very end you have some tape backup which are still used today, which can then store some terabytes of data, but they are really, really slow to access that data. But those are really, really cheap, and you can store large amounts of data. So, okay, so whenever you go out of the random access memory zone here, like accessing your hard drive, so some files residing on your hard drive, this is really slow compared to your ordinary computations, and therefore you should reduce it to a minimum if you're interested in performance. More details in one of the next lectures where we talk about high performance computing. So let's write some text files using the off stream, or aka the output file stream. So whenever you wish to write some text files or read some text files, you need to include the header fstream for file stream. And then it's really, really easy to use. So let's have some example data. Let's have a string which goes by data is : space, and then we have an integer 42. And now let's give ourselves the task to write that data to a file. How you would do it is you would create a variable which you call OFS. I mean, again, just a variable name, and the type is the output file stream type. And the output file stream, you give a file name, and then it will create a file with the following name on your system. And you can, for instance, also the output file stream has some useful member functions. So once you use the constructor to create such a file, the constructor also tries to create and open that file. But just to be sure, you can ask, is the output file stream variable, does that variable refer to an open output file stream? So you can ask, is open, and if that thing is open, you can write some data in it. Because how does it work? So you could use, for instance, the left shift operator, and you could just shove in the string literal to the output file stream, and then hello world exclamation mark new line would be printed into that text file here. You can also then append the string and the integer. You can also write those pieces of data into the output file stream, and then you can close the output file stream, and then your data is written. I mean, you can, for instance, still check if it's still open, but it should be closed after the call to close, obviously. And then if everything worked well and fine, then you have a file, a text file by the name of myfile.txt on your machine, and it contains hello world, and data is 42 in text, plain text. So what this code does, it opens the file stream, it writes formatted data to the file stream, it closes the output file stream. Open might also be used instead of the constructor. I mean, the constructor, if you give it a file name, it directly creates a file and tries to open it. Also, that would be possible. You could also use a default constructor receiving no arguments, and then you could explicitly call open and give it a file name. So that would be an alternative. And close, again, here is not really necessary, because those output file streams, or all the file streams, are implemented in RAII, so resource acquisition is initialization, which means once you use the respective constructor to initialize a variable, it will automatically open that, as you see here. And also the destructor will be defined such that it closes the associated file once the variable goes out of scope. So you don't really need to use close explicitly. Whenever the OFS variable here goes out of scope, the file stream would be automatically closed, because it's just defined in the destructor. That's the great thing about destructors, right? So you can not only initialize stuff and delete stuff, but you can also open files, and then in the destructor you tell it to close the file once that thing goes out of scope. Same holds for database connections, which you can then close, so you won't forget it. Yeah, that's what I just explained. Okay. Yeah, I mean, one thing, one use case where you could use explicitly is if you have a very long scope and a long running process, then you might also wish to close that file handle explicitly. What else do we have? We can also add some mode, some writing mode. So we have an output file stream again. We give it a file name. And usually, if you just close the if you close the constructor here, and you for a second, please ignore that one here. Then a new file with that name will be created onto your system. If a file by that name, myfile.txt, already exists, that file will be overwritten. So be very careful when you implement stuff like that. If you already have a myfile.txt on your system and you write something like that in your code, it will just overwrite that file, and it will remove your existing file. However, if you give it an additional open mode, which you can use here off stream, and this is some enum type, if I recall correctly, app for append. So if you chose the append mode and no file exists, then it will create a new one, And on the other hand, if you already have a myfile.txt onto your file system, it will open that and it will append everything that you write into that file stream. It will append to the existing file. So that append mode might be very useful to you. And then again, you can store some data and write some data to that file and do stuff. Yeah. Okay. So you have also different open modes. You can look it up what it means and which open mode can be used for what stuff. But usually the most useful things are append to an existing file, or yeah, just don't use anything and then it will just create a new blank file, and if a file already existed, it will be removed and then you have your new file. Okay, that was basically pretty much it about writing text files. So let's have a look on how to read text files using the if stream, so the input file stream. Let's have a look on how that is done. Still, you need the header file fstream. Let's have some code. Let's have some string line because we are using a very special function. Let's have an input file stream. Here we create a variable myFile of type input file stream. We give it a string, literal, and it will then try to open a file by that name. And here we should probably check if that file could be opened, because if that file does not exist on your file system, yeah, such a file couldn't be opened, so unable to open files. So here, whenever you need to write or read files, you probably wish to be very careful on what you do in terms of error handling. Here in the else branch, of course, this file couldn't be opened and probably the file doesn't exist, or you don't have the access rights to access that file. That could also be a potential reason. Otherwise, if you could open that file, you can now, of course, read data from it. And there's a great construct how you could do it. There's a function called getLine. GetLine receives as a first parameter a file, the file handle, basically, my file of type input file stream. And as a second parameter, it expects a reference to a string. And here we just have allocated a string on the stack and we give it a reference to that string line. And getLine will now read the first line of characters until the first \n, until the first new line. I mean, makes sense because the function is called getLine, so it will get one line at a time. And then you can do some stuff with that line. The line will be stored in that string. And the return value of getLine is used to make such while loops possible. So because you can now, in a while loop, read all lines of a file line by line, one after the other, and each line will be available to you by that string, because getLine will read a line from that file, will put the data in the string line, and then it will read the next line because you have it in a while loop here. And then you can, for instance, print each line to the command line again, just for a showcase here, what you could then also process that data and do something useful to it. So what does this piece of code do? It opens an input file stream. It reads a text file line by line until the end of the file is reached. And for that job, getLine might be the most used function for reading text. Yeah, it reads the stream until it hits a new a break line, \n. And afterwards, if the input file stream variable my file goes out of scope, the input file stream is closed. Okay, that's pretty much it about reading text. But now you can also read formatted text files, and maybe let's have some examples, because I learned that in computer graphics, so this is stuff that the guys in computer graphics did in order to store data or to read data in a formatted way. So what you do is my numbers input file stream variable, so try to open that my numbers.txt file of type input file stream again. We check if that file could be opened. Otherwise, yeah, we do some error handling here. I mean, for this example, we don't really care, so we just assume that this can always be opened. Here we have get line, so we read the file line by line. Observe that we are, rather than using a while loop, we can now use a for loop as well. And we can have our string line variable directly initialized here in that initial part of a for loop. We can then, as a condition, we can read lines. So we can try to read a new line from that input file stream, write it into the string line. And I mean, this is the condition of the for loop, of course, that is evaluated. And then we have a third part of a for loop where we usually do some action. So we increment some loop counters or whatnot. But in our case, we don't have to do that because getLine will automatically return or evaluate to false once the end of a file has been reached. So this would be another way, maybe even a more convenient way, rather than the for loop, using the while loop here to read a file line by line. What you could now do is to read the formatted data. You could, from that string, from that line of that file of type string, which you just read, you could now create an input string stream variable, ISS, so input string stream. And this input string stream allows you to read structured data from a string. So here an example, let's have two integers, a, b, and c, which we will be using to hold the results. And from the input string stream that we created from that line, we can now read three variables. We can read data from that string stream and try to initialize the variables a, b, and c. And as long as this works here, it's fine. Otherwise, if it doesn't work, we break here. And if that succeeds, we can print a, b, and c. And a, b, and c are now integers correctly initialized by the data that we just read from that line. And the idea in the first place is that you wrote some triples to the file in the first place. So you have a file containing 3 integers in one line of that file. So you have a file, text file, and each line contains 3 integers. That's the assumption here that's being made for that code. And once you have such a structured file, you can now read in the data in a structured way by using getLine and an input string stream, and you can read into variables a, b, and c. So again, what does that code do? It reads the file line by line for each line in the an input string stream is created. And the input string stream can then be used to read formatted data. Here we just assume that each line of that file contains 3 integers. Yeah, it's a really nice way and convenient way to read formatted data. But be very careful here. We haven't done any error handling, so that is really rather naive. So it's very fragile if the file that we give that program is ill formatted. So you would need additional error handling, but just this small, this should just be a small example here, of course. Yeah, that was pretty much it about reading and writing from text files. You can also read and write files in blocks rather than using something line-based. And the problem is that reading and writing line by line might be slow if you have some larger files. So that's really not suited if you have some files which are several megabytes or even gigabytes in size. Then that is not the preferred way to do it. And the idea of reading and writing files in blocks is that files are no longer read and written to line-based, but here you read and write whole blocks, so one or more blocks, which are raw bytes, which is usually much faster to read and also much faster to write. And of course, the fewer blocks you're reading, the better. The overall idea is, in the case that we open a file, that we determine the size of the file, that we allocate a buffer in the main memory, because I mean, once we have data in the main memory, we can actually perform computations with it. So the idea is determine file size, allocate some buffer in the main memory, in the RAM, random access memory. Then we read the data from the file into that buffer, into the main memory. And then we can manipulate that data in the buffer. So we can then read and write from the buffer and fiddle around with it, do some useful computations. And eventually, once we are done with that, we can write that buffer back to a file. And we are done. And we just had to read one block and had to write one block, which is much faster than line-based file manipulations. Here's some example code. And this, if I recall correctly, this code uses a bit of a hack, but let's see. So if the program here receives less than 2 command line arguments, we return directly. So this program is being expected to be given a file name as a parameter. That's the idea. So what we do is we have an input file stream is the variable's name. We try to read whatever the first parameter of the program is. So again, in reality, you would do some better error handling, really. And the open mode should be binary. So we wish to read the raw bytes. That's our idea. And then we check if the file could be opened successfully. And this is another trick. So rather than calling is.open in order to check if the file could successfully been opened, the input file stream also overloads the so-called cast operator. So a variable of type input file stream can be casted to a Boolean. And this can be done implicitly. So you can look it up on Google, the C++ override implicit cast operator. So when you create your own data type, you can override the implicit cast operator such that your data type can be casted to something else. And here, the is variable or variables of type input file stream can be automatically casted to a bool such that such expression works here. So that means if that file could be successfully opened, this thing here will be implicitly casted to true. Otherwise, it will return false. So again, just Google for the implicit cast operator, and then you can even override it for your own data types. Again, the idea is now we are looking for the end of the file. So starting at the beginning of the file, we look for the end by using the seek function. Once we found the end of the file, we ask, how much bytes is that file? So we are using the member function tell, which gives us the number of size in bytes. So size is the number of bytes that this file comprises. Then we need to set the file reading head, so to say, or how should I put it in a better way? Just give me a second to think of that. We need to set the file descriptor back to the beginning of the file. That's probably a better way to put it. So at first we look for the beginning, we look for the end, we then see, we ask here using the member function tell how many bytes we shifted that file descriptor, and then we set the file descriptor back at the beginning, and we now know the file size. That's the idea. Then what we do is we allocate a buffer. Now we need to allocate a buffer in main memory, and we just do that by using a string, or I should rather say we misuse a string. So we now misuse a variable of type string as a buffer, and by the way, we are also calling that variable buffer. And we use a somewhat special constructor of a string. We use the constructor that takes the size in bytes. So size is here the number of bytes of that file. We add 1 to it for the final null terminator. and then we give it a character, and this is the special 0 symbol, so to say, so that zeroes out each byte in the string. So what this line does, it creates a buffer of type string of the size plus 1, and it sets each byte of that buffer to 0. That's the meaning, essentially. And what we now do is we can read raw bytes from the input stream by using the member function read. So input stream.read. And it now reads bytes, and now we give it as a parameter, we give it a pointer where it should write down the bytes that it just reads. And if you know how a string is implemented internally, you know basically that it's a pointer to a character, and then it's a size, basically. That's how a string is implemented. Please remember how you implemented your own vector. It was also a pointer to some double array potentially, and then a size, and this is pretty much how a string is implemented as well. So we can ask the string buffer for its pointer. So the buffer is already initialized, and we now wish to get the pointer to that internal character array which is stored within the string. Unfortunately, first of all, we can do that by calling data, and it gives us the pointer to the first character of the internal buffer here, which is used to store stuff in the string. Unfortunately, data returns a const char star, and of course we can't write to const. And what we can do is, because it's a pointer and the underlying type is not constant, we can just cast the constness away. We can just have cast it to a char star, to an ordinary char star, and then we can write to it. So we ask the input stream here, please read a number of bytes and store them under this character pointer. And how many characters, how many bytes do we wish to read? Yeah, size of kind. And this is here what we determined previously. And what we can now do is we can print the whole buffer, and it will just print the string's contents, which now contains the contents of the file. So you can try that at home. It works perfectly fine. And by the magic of RAII, we don't have to close anything. So first of all, whenever the buffer variable goes out of scope, it will be automatically cleaned up. So the dynamically allocated heap memory that the string manages is automatically cleaned up for us, which is the reason why we used string, or why we misuse string as a smart buffer in the first place, because string manages the memory automatically for us. And then also, whenever the input stream variable goes out of scope, the file is automatically closed. Everything works perfectly fine. And then you can, here in between, before you leave the scopes, you can of course now modify and use the data which you just read into the string buffer here. That's the idea. Yeah, and this is to be considered a bit of a hack, but what can you do? So as a last part, so not reading blocks and writing blocks, as a last part for the really large files, like sometimes you have files of size of several gigabytes or even terabytes, and apparently if you don't have that amount of main memory, you can't read and process a terabyte file, which is a bit unfortunate, but sometimes you still need to do it even though you don't have that main memory, the amount of random access memory. And for that thing, there exists something which is called memory mapped files, which I present the idea to you, and I'll show you some code examples over which we go in brief, because if you ever need to do that, yeah, just look it up yourself. It's not that commonly used, but sometimes you need to be able to know how to pull that off. So, reading huge files is expensive, and there's another approach which is called memory mapped files. And what's the idea? The idea is that you map a file, or if the file is too large, that you map only portions of a file into much faster main memory, random access memory. So the idea is basically that you have a huge, maybe terabyte size file, And the idea is that you create kind of a small window in main memory, which now can move over the file that is of huge size that you don't really wish to read in a whole as a whole in the random access memory. So you now kind of have a window which can shift and move over that file, and you can now access portions of the file at least through that memory mapping here. So in good old C, you will just use mmap, which is a somewhat complicated function which can be found in that header file. But because this is not a C course, you would probably use something of some library code here. In C++, you would use a boost mapped file. We will have one lecture still where we discuss about libraries, how to use libraries, and what useful C++ libraries there are in practice. I will present some useful libraries to you and show you how you use them. And yeah, for now it's good enough if you know that Boost is a large C++ library that provides you with functionalities of all kinds. And so you also have such memory mapped functionalities. And this is useful if you have really large files. How do you do it? I just show you the code and briefly go over it. Here. Okay. So you would include some Boost files. So Boost IOStream device mapped file. Then in essence, what you do is you set some file parameters. So you set some parameters, of course. Where do you have the file? Here you have your mapped file. For instance, you can open it in read-only mode, such that you're not allowed to write. And then you set everything up, and then you can access your bytes, your constant data as char star. So you can really access the bytes of that file. And you have kind of a frame around your file, or at least around parts of your file. Here you can set the size of that frame, basically. Yeah, it's a beginner's course here somewhat, but that is the reason why I won't go into details. If you ever need to do that, just look it up. And yeah. You can also, of course, write files with a mapped file. Here is the example. Again, please look it up if you ever need to use that. Yeah, won't go into details here. So yeah, now the question remains how to read your files. I mean, it depends on your problem and your file size. So usually, as a good rule of thumb, files up to several megabytes can be read or written from line-based. Yeah, use the left and right shift operator and get line and all that good stuff. If you have some files up to several hundred megabytes, gigabytes or whatnot, even you can use a block-based file manipulation. You can allocate buffers and then read and write whole blocks. And if you have really large files, you would use some memory mappings. That's the idea. Now we have one more point which is probably interesting to discuss. That's about pretty much raw data, right? So, but C++ is an object-oriented language. So isn't there also a way to store the state of a whole object, but without having to to store and restore raw data, so to say? Yeah, and this is possible. There's a mechanism which is called serialization, which can be quite handy from time to time. So what is serialization? It's basically the concept of translating data structures or object state in a format that can be persisted. So basically what you can do using serialization, if you have an object of a type, so say you have a variable of type x, rather than maybe x has some integers in it, rather than storing the individual objects by using serialization, you can store the concrete object. So you can store the variable of the type x directly, and you can also restore it, and then as a result you have a variable with the same data that you stored. You can reload it from memory or whatever. Here we will have some examples on that. So the basic idea again is to transform the objects and the data contained in those objects into a one-dimensional bit string. So you serialize it. And then you can usually store it. You can store it as a file on a disk. You can store it in some memory buffer, maybe even. You can also transmit it across the network, and then on another machine, you can then restore and deserialize that data to obtain the exact object that the other guy has written and sent you. That's the idea. Exactly. So the restoring of serialized stuff is called deserialization. Can be done on the same computer, can be done on another computer if you send something over the network. And whenever something is restored, a semantical clone is created from the stored state. And this is really useful, for instance, if you need to store some intermediate results, maybe, so that happens quite often. If you wish to implement some caching mechanisms, so that can be really useful in such scenarios. In general, serialization and deserialization is very simple for plain old data types, so pod types, which only contain built-in types, like int, double, float, whatnot. It can be arbitrarily complex when dealing with pointers or reference. So if you have some more complicated data structures, like a graph which has some pointers to nodes, and those nodes again have pointers to other nodes, then it's really hard to do it. Can be done, but it's getting harder if you have more complex data structures. And because we don't have to reinvent the wheel, we can also just use a library for doing serialization. And one library that implements that concept here is Boost. So here's an example how to use text serialization using Boost. So what we need is, of course, file stream, because we wish to write and read something from and to file. We need, when we use text serialization from Boost, we need to include Boost archive text or archive, and this is for output archive. And also, if we wish to restore something, we need an input archive as well. So how does it work? Let's have an example. Let's have a class vec3 which contains 3 double variables x, y, and z. So that's a pretty easy to understand data structure or type. And now let's say we wish to be able to serialize variables of that type. So first of all, let's have maybe 2 constructors. So we can, as ordinary, we can have some ordinary constructors, so default constructor, and some constructor which receives 3 parameters used to initialize the data members x, y, and z. We also have the output stream operator, the left shift operator here, overloaded. And now we need to implement a special function such that Boost knows how to serialize and deserialize our data type. So how that works is we need to implement a function called serialize. As the first parameter, it gets a reference to an archive. And it also gets a const unsigned integer for the version. So that's just how it is. So the serialize function just needs that signature, because it's then later on used by Boost. And in order to append data to the archive, we can now use the what was it called? The ampersand operator. So we have that archive here. We have the reference to an archive here as a parameter, and we can now shove some data into that archive. So we use ampersand, which has been overloaded by the Boost library to do exactly that thing here. So we can now write our 3 double values x, y, and z to that archive. We also must make the serialize function a template. and here the archive can be used interchangeable. But that's what we need to do. And we also need to give a boost access to our class. So we can declare a friend class, which is called boost serialization access, and we grant access to all the private functionalities and data to that particular boost class. So by declaring another class as a friend, this other class here can access all the private stuff of our own data type here. And okay, that's already it. Now you can serialize and deserialize your vector. How does it work? Let's have an example how to use it. Let's create a vector v1 using the values 1, 2, and 3. Writing it to the command line, just to be sure. We can then create an output file stream. So we can write the data to a file. And what we do is we now create a text output archive, OA, which receives a file handle, basically. So we now create an output archive, and we give it the file handle where it should store stuff. So and the text output archive could also receive some other streams. So it does not need to be a file handle. You could also plug in a network connection or something else. And now we just use the left shift operator to shove the contents of v1 into the output archive. And this operator here is overloaded such that it calls this serialization function. This is just one function. So, and then we go out of scope. That means the file is closed and the variable v1 doesn't exist anymore. It's cleaned up. And now let's introduce a new scope, and let's try if we can read it back from file. So what you do is you would create an empty vector, first of all, back3, which is supposed to hold our results later on. Here you open your file for reading. You use a boost input archive and give it the file it should read from. And then you just read from the archive and use the input archive to restore the state of that vector variable. And if you then print it again to the command line, new v1 will print 1, 2, and 3, because that's the data that we stored serialized into that archive, and here we are now reading from that archive. So that was a text serialization. There's also binary serialization. Then you don't need to include text output archive and text output input archive, but rather you need to use a binary output and input archive. Other than that, it's pretty much exactly the same. So you can try it out. Here, of course, you use, instead of text, you use binary. And probably you don't wish to name the file and end it with .txt, but rather you maybe bin or something, such that you denote that this file contains binary data. So nobody comes on the idea that he or she could open it with a simple text editor. That wouldn't make too much sense. So yeah, again, you can try that out. That's quite interesting and quite useful. Oopsie. And other structured text serialization formats are, of course, also possible. You probably know about XML. You probably also know about JSON. Those are structured text serialization formats that you can also use. If you are interested in the boost input output archives, you can have a look here on boost serialization. Also, if you wish to use the boost libraries, you need to link against that. So if you have a program here, you need, using the -l, you need to specify the libraries such that your program also links against the appropriate boost library, such that your linker finds the boost functions, the functionalities implemented by boost. We will talk about how to link against libraries and such in one of the next lectures, where we talk about libraries, useful libraries. I will present you some examples. So maybe let's briefly discuss about the pros and cons regarding text versus binary serialization. So first of all, you can use text serialization, plain text or XML or JSON. So you could either store it in plain text or use some structured way. It's human readable, which is probably quite nice. You don't need any extra debugging tools because it's just text. It's independent of any computer architecture because, again, it's just text. You don't have any size of issues, such that if you write an integer in text, it's just the text version of that integer. If you would write an integer in binary, maybe I write it on my machine and my operating system is, or my architecture is 64 bits. Register width, and maybe you have a old 32 bits register width. Then you have some size of issues depending on the platform and architecture. So that does not happen if you use text. Also no little versus big endian issues. If you don't know what that means, doesn't matter. If you wish to know what that means, you can look it up. And it can also produce smaller results when most of the numbers that you are going to store are small. For text, it doesn't really matter. Binary typically uses fewer CPU cycles because that's then the machine doesn't have to do any conversions. So it's faster, more performant. That might be interesting when the input-output is the bottleneck of your application. It also lets you ignore the serration between adjacent elements or adjacent values, since most values have a fixed length. So whenever you write some data as plain text, you need some spacing or serration. Maybe you use a semicolon to denote, this is where one integer ends and this is where where another integer starts. If you write in binary directly, you don't have to do it because the integer is a fixed size bit has a fixed size on the machine, and therefore you don't need to use any serration elements or markers. It can produce smaller results when most of the numbers that you need to store are large. It's unfortunately dependent on your computer architecture. So if you and I have different architectures and I would send you some binary format and then you would try to restore it, you may run into trouble, and it's unfortunately not a very good thing. In general, no right answer. You have to see what your use case is. Notes on serialization is easy when using simple data structures only. For instance, our vec3 was a very simple type. It gets really much more complex if you have more complex types. So if you need to serialize derived classes in a type hierarchy, that might get a bit tricky. I mean, it's still possible, but it's just more effort to get it right. Also serializing classes that contain pointer data members or references, such as lists and graphs, that can also be a bit tricky, but I mean, it's still possible, of course. Luckily, we have some library support. So if you have some built-in arrays and you wish to store built-in arrays, or you wish to serialize built-in arrays, Boost knows how to serialize built-in arrays. And luckily, Boost also knows how to serialize STL containers. So even if you have a type which makes use of some STL types, container types or whatnot, this is still very easily possible because Boost already implements all that stuff for the STL containers, which makes it quite handy to use. If you need more on that, it's all perfectly explained here by just looking at the Boost documentation. And this would be pretty much it for today. So we talked briefly about object-oriented programming and kind of finished that topic. We talked about typecasting today. What else did we do? We did talk about file input and output operations. So reading and writing files, how to deal with files in blocks if you have larger files. Also, we talked about memory mapped files. And at last, we talked about serialization. All right, thank you very much. That would be it. See you next week or in this afternoon's exercise class. All right, bye-bye.